So what kind of mark do you want to leave behind? I've got a story that might inspire you. It starts 40,000 years ago in a cave inside a mountain in the northern part of Spain called El Castillo. And if you look at the roof of this cave and you look a little bit closer, you'll see some marks up there, some artworks. And it might surprise many of you to realize that scientists are now beginning to agree that this specific piece of art was not created by humans. That's right, look again, count the fingers, and it's not what you're thinking. These were created by Neanderthals, or Neanderthals to use the correct pronunciation. And Neanderthals went extinct about 40,000 years ago, but notice how different they are to us. Look how much bigger their brains were like us. And if you could entertain me for a moment, if we wanted to write Nick Bostrom ancestor simulation, and imagine we did this in Java, we would create an abstract class called Homo heidelbergensis. Notice that the genes are private. And we would then extend that class to create a Neanderthal. Same thing for Homo sapiens, and our UML diagram would look something like this, and then 500,000 years later we'd add on Homo sapiens. So the two are quite different in that if we created an instance of a Neanderthal and an instance of a human being, Neanderthal does not equal human being, nor does human being equal Neanderthal. But they were a separate and intelligent species that lived on Earth many thousands of years ago. And, interesting unrelated side fact, humans could shag Neanderthals, and this did in fact happen, which leads me to my theory around where these handprints got onto that cave wall in the first place. But back to the point. Neanderthals implement a make-mark interface as well, and so do we. And this is what it looked like for Neanderthals, and we have our own versions of that. So back in the present day, I'd like to ask you how you want to implement your make-mark interface. This is a completely different type of cave painting. It's called the Pioneer Plaque, attached to the Pioneer probes 10 and 11. And while these were being constructed, pay attention to where that dish is being mounted on those struts, and if you had to peer between those, that's where you'd find the Pioneer Plaque. It's funny to me that they're actually pointed facing inward and not outward. But anyway, these were the first probes that humans sent outside of our solar system, past the orbit of Mars and past the asteroid belt. And Jupiter was one of the first planets that Pioneer 10 visited, showing us a photograph like this, which, maybe a story for another day, wasn't actually taken with a camera. But it's a misconception that Pioneers 10 and 11 used an Intel 404 chip. They actually had custom TTL logic, and that custom TTL logic could only handle about 200 instructions, with memory to handle about 5 in advance that could be sent from Earth, with approximately 40K or 50K worth of memory. So a very interesting mark that was left there. Later on, these were sent out. You might recognize these as the golden records used on Voyagers 1 and 2 in 1972, and this is from NASA's JPL website. It's a very cool 3D model that you can interact with, and it shows you exactly where they're mounted on these probes, so you can see exactly where they are. A little bit bigger than normal records, but if you wanted to play one of these, fortunately the instructions are on the cover on the front. So for anyone or anything encountering these, they'd first need to understand that there's a property of hydrogen where the state of the spin moments between the proton and the electron changes, and this can be used as a universal clock. If you match that up to give you the rate of rotation at which you should create your own record player to play this with, you can then be able to pick up the signals off that record and compose an image. And notice that calibration image, that circle down in the bottom. This is what it would look like or sound like if someone had to actually play that record. And there you've got that calibration image coming in. Very interesting stuff. And here's an image of our galaxy and what it looks like. This is what our number system looks like. And it carries on like this with pictures of various things from all over the planet. A lot of it is copywritten, so I can't show you a lot of it. And as usual, there's always some human genitalia attached to many of these things. That's why I'm barred by this conference's ethics and rules to be able to show you the rest. But there are also other interesting things like how we communicate with radio telescopes, and I especially love this picture of the Arecibo telescope. Here's a nice view of it from above, because when this was inaugurated in the 1970s, they sent out this very famous Arecibo message, and I raised this only because this had a fun little joke reply that came back called the Arecibo reply, which I thought was pretty funny. But anyway, the Voyager probes also had their own type of computer. They had three, in fact, the main one being a command control computer system. And this is what uplinked and managed all the procedures between all other types of computers. Again, this was custom TTL logic running at 2 megahertz, but it had about 64 kilobytes of RAM and approximately 64 megabytes of storage. And this is what the CCS looked like from the outside, some black and white photographs from the inside. And it was actually dual-core. It had two processors. Notice processor A and processor B. And notice as well that it wasn't actually any type of flash storage, but actually tape. It had 1,000 feet of 8-track tape that it used to store images and other data that it would later on relay back to Earth in a very slow connection of 168 bytes per second going up and 72K coming down. Now, the probe was programmed in a custom sort of assembly language that used 18-bit words with 6-bit opcode and 12-bit addresses. There were only 13 registers in total, and some of the software for high-level functions was written in Fortran and later on ported over to C. So of course we're not talking about Doom 2016 or Doom Eternal, and we're not talking about Doom 3 either. We're talking about the original Doom from 1993, and I'm sure a lot of you guys are asking yourselves, but why? And that's because Doom really is special, because Doom was impossible. If you think of the best computer hardware you could buy for yourself at the time, this is an example of a Onyx by Silicon Graphics that could cost you anywhere between $100,000 and $200,000. And in 1995, a computer like that was used to develop Toy Story the movie, which required 117 Sun Microsystem computers in racks like this, 800,000 machine hours, to render 114,000 frames of animation that all looked like this. Compare that to what Toy Story 4 looked like last year, and look at the detail on that. You really do get a sense of why, at the time, Doom really was before its time in pretty much every possible way. So, I mean, if you think about what Doom looks like and what you could get 2 years before Toy Story even came out, in real time, on a computer that wasn't even designed to produce 3D graphics like this, it really is amazing. I mean, consider you could run this on, well, at an absolute minimum, an Intel 386 clocked at 33 megahertz and only 4 megabytes of RAM. There was no need for a graphics card, and they didn't even exist, not even in their first versions. That's what things like Quake ended up encouraging in the market. For most people, this is what computers looked like, and this is what Microsoft Word looked like. So way back in February 1992, some of the first Doom alphas were released. So some of you may never have seen these. This is what the main menu looked like. There's this weird heads-up display. This is this kind of space marine base and a weird bayonet attached to the front of this gun. And on the 10th of December 1983, on our Software Creations BBS, 2.39 megabytes of data was uploaded to a University of Wisconsin-Madison server. And it's a myth that the server actually crashed. What really happened is that so many people were expecting Doom that it had filled up the entire connection pool for the FTP server, and they had to phone the admin up to go and restart the server so that the guys at id could actually get a connection and upload Doom. But after that happened, everyone started playing Doom, and it was a major success. It started earning id Software $100,000 a month. John Carmack and John Romero both bought themselves matching Ferraris, and multiplayer became this huge thing, although back then the term deathmatch was of course coined, and this was the deathmatch manager, and I remember using this with a serial cable to connect my computer to family members or to friends to play deathmatch games, which I spent way too much time doing, and at least things didn't get too much out of control. But there were articles like this in things like PC Magazine, where Doom took over my life. It makes one think of World of Warcraft, actually. But it's absolutely true that Doom was banned in places like Intel, Lotus Software, and many universities. And by 1995, there were over 10 million installations of Doom. meaning that there were more installations of Doom than there were of Windows 95, which was one of the things that prompted Bill Gates to make this very strange promotional video promoting Doom 95, which was meant in turn to promote Windows 95 as a gaming platform. But of course, It Runs Doom became this massive phenomenon, and I love this comic where this computer scientist is talking about this alien computer that has an architecture entirely foreign to ours. We have much to learn from it, and we may have much to fear. And a computer scientist saying, bam, I've got Doom running on this thing. And this trend is so much fun. This is Doom running on an iPad, Doom running on a Canon printer, Doom running on an Apple Watch, but don't worry, Android fans, we've got you covered. Doom running on the touch bar of a MacBook Pro, Doom on a Kodak digital camera, Doom on a PSP, Doom on an ATM machine, Doom on an oscilloscope, Doom on a barcode reader, Doom on the entertainment system of a Porsche 911 Turbo, and Doom on a toaster. I think those last two were, probably fake. But are you convinced that there must be something about this software that makes it easy to port and just something worth looking into and something worth learning about? And this is why I'm proposing that Doom might just be the ideal candidate to leave on a rover like Curiosity's, especially because the story of Doom starts on Mars, and it's probably also as much of a cultural artifact of how we got to this point over the last couple of decades than anything else. So at this point, it's probably a good idea to introduce some reference material, and a lot of what I'll be talking about today is based on two books. First, the game engine Plaque book for Doom by Fabian Sandglad, and this goes into a lot of the detail around how the code was put together and how various different parts of the game engine worked. So that's really, really recommended. And if you're interested in other titles by Fabian, like his books on Doom 3 or Quake, I'd highly, highly recommend those. But I've used this extensively as reference for what I'm going to be chatting about today. And then from a more cultural story about how Doom came about, Masters of Doom by David Kushner is a very, very good read. And by the way, if you do grab the audiobook version of this, it is read by none other than Wesley Crusher. So, who made Doom? id Software were these guys who actually started working in this lake house, first developing Commander Keen and then moving on through other titles like Wolfenstein and Doom. And the two main characters we'll read about in this story are both John Romero and John Carmack, neither of whom came from, wealthy families with grand houses. They actually came from broken homes and didn't have fancy educations. But looking at John Romero, he was the principal artistic influence on the game, I suppose, and a lot of the development around the level editors and level designs and those kinds of things, where John Carmack was really the brains behind the development of the engine that ran Doom. So he was developer squared and created the 3D engine and really wasn't shy in using a lot of reference material and academic papers to get the maths right behind what he wanted his engine to be able to do. So in 1983, the Nintendo NES came out, which, by the way, can also run Doom if you make some very serious modifications to one of the cartridges and put a Raspberry Pi in it. But the NES was most popular for running games like Mario. And I just want you to notice how the background can move as Mario moves here. That was something quite unique to consoles at the time. And even 7 years later, in 1990, the PC, for example, running a game like Prince of Persia, just notice how, while Prince of Persia was fun, you probably never noticed that the background never moved, because it was very expensive for a PC to redraw the background every single time. And that's why they looked like this, and why most PC games looked like this. But enter on the PC Commander Keen in 1990, and there's a VGA version of it. And if you play this game and start a new game, this is what it looked like. And notice we have a moving background. And you need to understand that this was quite revolutionary for the time. No other PC games could do anything like this, and this is what id Software was able to do. But how did it work? Well, if you take your normal screen resolution for a PC of the time, you only had 320 by 200 pixels to deal with, and every time you as a programmer wanted to write a piece of software that would render a game like this, you needed to render the entire screen, put it in VRAM for it to go out to the display, and then for every frame you'd have to redraw the whole screen, pop it in VRAM. Same thing, you get the idea. This is not terribly efficient and why it generally wasn't done. Enter adaptive tile refresh, which was a VRAM hack, an EGA-based VRAM hack, where you'd put the whole image into VRAM and then just reference it by its XY coordinates to be able to move it around on screen as follows, and thus you could get this kind of gameplay. So by 1992, Wolfenstein 3D comes in. And here's just a little bit of video of how this thing looked. I love that get psych thing. Let's go start a new game there. Bring it on. Love that loading screen. And you'll see a lot of common elements with Doom and what Doom looked like. But also want you to notice, besides how sort of pixelated everything looks here, that Wolfenstein only has walls in its environments that have 90 degrees. You don't get any other kind of things, which is why this looked like such a maze game. And well, anyway, we can just carry on. How did this work though? Well, it used something called ray tracing, where we would literally cast a ray from the player's perspective and measure the length of that ray. And if you looked at that from the player's perspective, it would use the length of that ray to draw a series of columns with the height changing depending on how far away the ray came. And well, it also came with the advantage of you only needing to draw that which the player could see from their perspective. And this is what was called ray casting, not to be confused with ray tracing. That's what you need one of these for. So Doom's source code was released to the public in 1997. And for those of you guys who still play Doom on DOS, if you had to ever dir out that directory and see what's in there, you'd notice that the biggest files were always the executable and the WAD file. Now, the WAD file would be quite big. It would make up almost 90% of the entire game. And WAD, of course, stood for where's all the data. And if it had to break open one of these, you'd find that only about half of it was graphics. 10% of it would be sound, a little bit of sound effects, and a lot of it, almost 30%, would be map data. And if you looked at the WAD compared to the actual source code that was released, the source code that was released was only for the game engine itself and not the actual WAD file, meaning that you still needed to pay and get the WAD file to use with any open source solution that you created around that. So without any further ado, let's take a look at the source code itself. So the source tree starts with Doom v1, which was initially released in 1993, and then there was version 2, from which things like Heretic and Hexen and all those games were created by Raven Software. And then Doom carried on up until Doom 2. You've got to love the versioning number over there. And then Doom 2 got a patch. Ultimate Doom was created. Final Doom. Doom 95, you saw that thing with Bill Gates. And then Linux Doom. And Linux Doom is unfortunately the only version of this for which we have the source code. Why, you ask? Well, it's because of DMX. Not this DMX, but because of DMX lib by a company called Digital Expressions. Now, Paul Raddick at the time just said, sorry, but that's the way it's got to be. And John Carmack described it using the DMX sound library as a mistake. But John Romero was more vocal, calling the guy a shithead and a soundcode dork. But anyway, now we've got the source code up on GitHub, and you guys all know how to go and pull stuff off that. But if you do grab the source code and check it out, you'll see this map that's quite useful. It shows you where all the video system files are, sound system, networking, the renderer, etc. And if you use Visual Studio Code to explore this, you'll notice that this is written in C. So there's a make file using GCC, which you'll use to compile this. And yeah, I always like to go to the main entry point of any program that I'm going to look at to see how it all works. And interesting how you can see all the different parameter options that you might not have seen over there. Things like no monsters, fast monsters, deathmatch, alt death, interesting things over there. And of course, this is what it would have looked like if you were studying the code, or what it probably looked like for not the original developers. They use next step systems, but what it might have looked like in something like Borland. But anyway, yeah, if you try to compile this, you'd probably have an issue building it, because modern compilers are all 64, but you'll need to do a lot of configuration to get the make file to do a 32-bit compilation for you. But one way to get exactly the same experience as what you would have had back in those days was to use Red Hat. Now, I do know Red Hat is a sponsor of this conference, but they're not paying me to say this at all, and you'll see why in a moment. So I'm looking at a copy of Red Hat from 2000, specifically version 6.2 called Zoot, that I ran in a VM to get this going. And I wonder how many of you have noticed the Netscape Navigator icon down at the bottom there. But anyway, if I wanted to compile this, I would open up a new terminal. If we zoom in just a little bit over there, this is the process you'd go through. So there's all my source code over there. And I would just need to create a Linux directory. And in that, I've put a Doom2 WAD file, which is what I'm going to need. And then when I press make, or rather type make, I'm going to see the following output. And this is that make file busy building up our version of Doom, which we've now compiled. So if we go check back in our Linux directory, there's all our O files and our Linux Doom copy. So if we get that running, that's Doom starting up. That should look familiar to you. And there it is. It does mess up the graphics of the session, but the graphics of the game itself are perfectly fine. And it plays perfectly fine too. So I can just start a new game over there, and there we're going. So let's chat a little bit about how Doom works inside, specifically binary space partitioning, which you might have heard of before. So you might recognize this map. This is E1M1 from the original Doom. And if you considered the entire map as, say, root node A in your tree, you would then take your map and cut the whole thing in half and partition it into two, thus leaving one side on the left and one side on the right, and those would become A and B in your tree. And you'd then go and partition side B and create C and D in exactly the same way. And you do this until you've gotten the entire map partitioned this way in small, manageable segments that you can search through very easily in a tree. Now, if you've never used FlameGrass before, I'd very much recommend this for any type of code profiling that you want to do. But notice how, with the main loop down at the bottom and Doom main that we saw before, it calls display and then render player view and then draw planes and then render BSP node. And it does this 30 times a second. This is why Doom's frame rate is fixed at 30 times per second. So if we're going to parse this or traverse these BSP trees, we would go to point on inside, which is one of the parts in the code. And notice at the bottom there that we are busy. We've got a left and a right side of these fixed T objects, which are essentially the nodes in our tree, which would later on call render player view, which would then call display. And if you scroll down there a little bit later, you'll see there's render player view, the HU drawer, that's your heads-up display, and full background screen. And how this would actually work in practice, if you imagine a player's position and a player view that we need to render, we would have a segment that we'd need to draw, which would have its own XY coordinates for the two sides of that segment. And on the screen, we would use the same raycasting technique to determine the height of the columns of those two pieces. And then we'd do some calculations to create a view angle box to be able to determine what that segment should look like. So if we had to move around inside a map like this and then stop, this is what the actual rendering would look like. And notice how it's rendering the things that are closest to us first, because it's not going to waste any CPU or processing power rendering anything that's further away. And then it renders stuff in the background. And this is going to be the draw planes method that's drawing those bottom, like the floor, ceiling. Well, there's no ceiling in this scene at least. You can see it draw everything up there. So that would all happen 30 times a second. And this would be the render player view that's doing all of this. And view draw planes. Plane drawing is also a little bit interesting. So here's just another view of the same thing happening. But yeah, let's give this a second just to run a little bit. I should have sped this up, I'm sorry. But there are the planes being rendered as well. And it's interesting how it does them as triangles in some cases. And again, everything you're seeing here is slowing down. And this would be drawn 30 times a second. Oh, and speaking ahead of its time, this is really interesting. It only works with Doom version 1.2. But if you've got 3 computers all networked together, either via a modem or preferably a serial cable in this example, Here's an example of this being done in, not VirtualBox, DOSBox actually, is where you would be able to play the game with 3 screens networked together, but it would show you the left and right angles. And this is something John Carmack did. So very impressive for its time. If you consider that this is 1993, 1994, immersive virtual reality was close to it as you could get. So it's actually no wonder that John Carmack ended up at Oculus working in 3D immersion and those kinds of things. So in 1997, the Pathfinder mission spent about 9 months getting to Mars and gets into the atmosphere, fires some retro rockets, lands on a balloon airbag-based system, and becomes the first functioning rover to work on Mars. So this is what the lander looked like. There's some stereoscopic cameras that gave some really great panoramas, and the rover itself was called Sojourner and would travel around and look at rocks and take little samples with a spectrograph. But we want to know what kind of CPU this thing ran. So let's take a look inside. This is all of the rover's circuitry, and if we zoom in, that is what the CPU looked like. And it's a 80C85, similar to commercial models that would look like this inside, and popular in things like the IBM Data Master from the 1970s, or the IBM PC XT, which some of you might remember from the early 1980s, that ran the very popular Intel 8088 chip and looked like this. But the 80C85 ran at only 2 megahertz. It had only about 70k of RAM and 512 kilobytes of storage. And the rover would communicate back with a kind of walkie-talkie system equivalent to a 9600 baud modem that, after error correction, only really worked at an effective 2400 baud. So the rover could in fact only communicate back to Earth in bursts of about 2 kilobytes up and 2 kilobytes back, sending photographs like this one. But what kind of operating system did this thing run? Was it PC-DOS that was popular in the early 80s, or maybe MS-DOS? No, it had no operating system at all. It used something called a cyclic executive, which in code is very much just an infinite loop. It's an alternative to a real-time operating system, and this is how all of the rover's functions were implemented in C. But does it run Doom? Well, I'm afraid not. We just don't have enough MIPS for this thing to run Doom. So in 2004, coinciding the same year that Doom 3 came out, a new pair of rovers end up at Mars, the Mars Exploration Rover, or sometimes called MER or MERS, because there were 2 of them. And these things landed in a very similar style, using retro rockets and airbags to bounce around on the surface. And this is how Spirit and Opportunity became the new rovers on Mars. But of course, you've probably watched a lot of documentaries and know a lot about these rovers, but you probably don't know what's running inside. So let's take a look inside. And if you were to disassemble one of them, you could draw out this PCB card. And what you'd want to be looking for in the top corner over there is its main CPU. And that is, of course, the BAE Systems RAD 6000. And it's part of the Power 600 microarchitecture. So this is basically the radiation version, or the radiation hardened version, called the RAD 6000. And then there was also a much earlier version, the IBM PowerPC 601 from 1992, so from many, many years before. And this CPU was actually quite popularly used by Apple in its first series of Power Macintosh computers, the 8100, and that CPU being clocked at 80 megahertz in 1993. So the rover had a RAD 6000, downclocked a little bit to 20 megahertz, 128 megabytes of RAM, and 256 kilobytes of storage. And the rover could communicate back to Earth either directly, at sometimes as low as 500 bytes per second, or use a satellite and go up to 256 bytes per second. But what's interesting is the operating system, which is a real-time operating system by a company called VxWorks. Here's just an example of what VxWorks 7, one of the later versions, looks like starting up. And VxWorks is, being a real-time operating system, doesn't work on processes, but more this concept of tasks, but we'll definitely get into that a little bit later. And it's just fun to note that all of the rover's control software was written both in C and C++. But in 2009, the Spirit rover was driving up a dune and sadly got stuck, and by 2010, it was game over. But I have always thought that that might have been an opportunity to upload some interesting stuff into that rover's memory before it was lost. And sadly in 2018, the surface of Mars was covered in a dust storm, and we lost the Opportunity rover as well. And as sad as this is, I do love and snicker at this tattoo with a sort of poeticized version of the last message that came from the rover. But notice that that is not the Opportunity rover, that's in fact the Curiosity rover. So would any of these have been able to run Doom? Well, if you look at the RAD 6000 against the absolute minimum you need to run Doom, being an Intel Thread 6, the RAD can do it. It's got 35 MIPS versus the minimum of about 11.4. And because it's clocked down on the rover to about 20 megahertz, it could still do it. So it would seem that we're in luck, but none of those rovers are running. So let's see what else we could use. So in 2012, something interesting comes to Mars, or something curious, let's say, and it uses this awesome sky crane thing, which is quite different and extremely impressive. And most of you have watched documentaries around this, but this is, of course, the Mars Science Laboratory, or MSL. And we want to know immediately, does this thing run Doom? So let's look at some system requirements. Well, we need to consider the CPU, the RAM, some hard disk space, of course, some networking, just to get some software on there, of course, what type of OS it's running, some power, and maybe a display, some sound, and a keyboard and mouse. So let's take a look inside. And this is what Curiosity looks like when you pop the hood open. And I know what you're thinking, but no, that is not a CPU cooler. It's the SAM, Sample Analysis at Mars unit, and it's actually what the drill deposits dust and drilling samples into, and it uses this kind of vibrating sieve where it can actually make a sound. And there's this story that every year on its birthday, Curiosity sings happy birthday to itself. That's actually not exactly true. It only did it once in 2012 or 2013, obviously. And I don't know, this kind of got me thinking about the difference in the atmospheric pressure between Earth and Mars being quite phenomenal. And I thought, well, maybe, just maybe, if you get the drill involved, you could do something like this. Some of you might recognize this. This is called the Floppytron. It's just a bit of a retro thing where, yeah, they've programmed this thing to be able to play MIDI files. I just thought that was a fun thing, but not probably. Let's get back to the CPU though, and if you're looking back into what Curiosity looks like inside, this is probably where you should be looking. And if you had to draw one of those cards out, eventually you'd find this one. And on that you would find the PowerPC RAD 750 CPU by BAE Systems. Now that's what it looks like inside, and no, it doesn't run at 200 megahertz as most people say, and what the spec says. On Curiosity it actually runs at 133 megahertz. It's got 256 megabytes of RAM and 2 gigabytes of storage, and it's actually got all of this twice because the rover has two different computers, A and B, and it switches between the two of them depending on whether or not one is giving issues or if they want to create software updates or anything else like that. So from system requirements point of view, we've at least got enough CPU, RAM and storage to maybe get Doom running on this thing. So I was thinking about how I could test this myself, and the PowerPC RAD 750 20 years ago costed $200,000 back in 2002. So in 2020, that's almost $300,000, or more than 5 million South African rands. So this got me thinking that the CPU is, after all, part of the Power 750 microarchitecture, which includes the radiation-hardened version, but also a Motorola version used by Apple in some of its computers, and by IBM. So if you look at the Motorola version, this was popular in the late 90s, early 2000s, and was also used in the original iMac. So I went out onto OLX and bought myself one of these for about $2.5 grand. Went onto Gumtree and got myself an equivalent laptop from 2001. This is an iBook 3G. And then I went on a bit of a rampage because along with the G3, I needed to get the G4 and the G5 because I needed all the PowerPC Macs. But that's probably for another talk and another day. But this left me in a position where I had some comparable systems that I could actually run this on without using virtualization or anything else. So I could rely completely on bare metal to see if I could get this working. Now, the operating system becomes another concern, and the Curiosity Rover runs VxWorks just like previous rovers, specifically version 6.9, not the latest version 7. And if I want to compile Doom for VxWorks, well, I went and got myself a copy of a much older version that uses VxWorks version 5. This is Tornado, that you'd use to create either a bootable image or a task that you could upload to something that's running a different sort of image. Obviously, it runs in Windows XP, just to kind of mess around with. And initially, I'm just going to speed this up a little bit, but I created my own little Hello World just to prove that I could get a task running in VxWorks, where I could be running Doom, or at least just, get something printed out. So at this point, it was time to add in the original Doom source files and start working on a VxWorks version of this. And, well, first you have to pull in the headers and then the C files, and I've sped this up as well. So, yeah, this is quite a good IDE for its time, I reckon. It helps you manage dependencies between different classes, but I quickly ran into some pretty serious errors and issues. And this was incredibly frustrating. If you just look at one of the first ones over here, look at that dthinkh line 48. And if you go open up the file, it does have a semicolon. I don't know what this thing's complaining about. It does have a semicolon. So I kind of gave up on that. VxWorks has multiple security issues in any case, and while we're not going to explore that in this talk, it is interesting to consider how many issues there are. But the makers of VxWorks also create something called Wind River Linux. And Linux is a good option. It would be able to run on this kind of hardware. So for the hardware I had in mind, I chose Yellow Dog, which was a derivative of Red Hat actually, and got that on my iBook and started messing around with that. So first loaded up my source files. Now I needed to make some changes that I'll chat about a little bit later to get this working on a PowerPC, because we are working with a big endian and not a little endian CPU. But if I click make, it goes on and creates an executable for me, and there you can see I've got a Linux Doom executable like I had before, and it runs just fine. The colors are a little bit messed up because, like you saw in the previous version where I ran this on Red Hat, every time I wanted to do a screen grab, it messed up the colors of the game, but it's actually the other way around. The game's colors look fine when you're actually playing and interacting with that X window. And of course, it ran fine on my iMac 3G as well and all of the other PowerPCs, and I've put this up on GitHub for you guys to take a look at and mess around with and contribute to if you like. So it really looks like we're making progress here. So why the massive price difference between a RAD 750 of 5 years ago and an iMac 3G that would have costed me almost 200% less 20 years ago? Well, the answer, Duke, is radiation. Radiation obviously pouring out of the sun, radiation that we need to deal with when we travel through the Van Allen belts, radiation as a result of supernova explosions in other galaxies and our own, and the general cosmic background radiation that emits tons and tons of particles out in space. And one of my favorite papers that I've found regarding this kind of stuff on the effects of radiation and specifically cosmic rays on DRAM came from a study they did in 2009 on some Google servers, and they found that for non-error corrected memory, the mean error rate amounted to 3,751 errors per year. So think about that the next time you have a bug in your software. But anyway, radiation hardening is of course what we're chatting about and why this is so expensive. And you get a bunch of different scenarios that can come up, specifically things like single event upsets, latch ups, and gate ruptures, which sound pretty serious. So let's take a look at why and how this kind of stuff works. Most of you would have seen a logic gate represented like this, and it's pretty much the hardware equivalent of what you could write in software like this. And yeah, if we take inputs A and B at the top there, if I put in 0 and 1, of course I get 0. If I put in 1 and 0, I get 0, but if I put in 1 and 1, I get 1. So how does radiation affect this? Well, let's look deeper inside a gate and see how to build one. And to build an AND gate, you'll need 2 transistors. And if we add some current in on this side and put a 1 in on that side, so we're adding in current from this side, it'll open the gate and the electricity will flow through to the next transistor. And if we put nothing in there, we get nothing out, which is a correct AND operation. And of course, if we do put some current in on the other B side, current will go in, it'll open up that side, it'll ground, and we'll get a 1, and our transistor works perfectly. However, if we wanted to zoom in and see what these things actually look like, everything's based on a silicon substrate, and if a high-energy neutron had to smash through the inside of this NPN transistor, the substrate would get damaged and we could end up with a short circuit between the two sides, and as a result our transistor would always be on. So if we tried to turn it off, this would be incorrect, and that would kind of show you all the different things that can go wrong with your transistor, and thus the massive price difference for all the proprietary techniques that companies like BAE Systems go to make these things cost as much as they do. So let's chat about power just for fun for a second and consider what type of PSU a rover like Curiosity uses. Well, it actually uses something called an RTG, or radioisotope thermoelectric generator, where it's got scalding hot plutonium-238 inside, and it takes advantage of that to create electricity. Plutonium, of course, having a half-life of 87 years, so it stays hot for a very long time, and using thermal couples in an RTG like this. This is Curiosity's actual RTG. It actually takes 4.8 kilograms of these square-shaped pieces of plutonium, but yes, that gets mounted into the back of the rover over here, and that's what gives it power. Very similar to what you see on some of the other Voyager and Pioneer spacecraft, where they're kept a little bit away from some of the instrumentation. So that at least solves the power problem for us quickly. So let's talk about networking, specifically the deep space network, and how we communicate with rovers on Mars from Earth. Now, at its best, Earth is only 54 million kilometers away, and it takes about 3 minutes for a signal to get there, traveling at the speed of light. But at worst, when we're on the other side of the Sun, it's 401 kilometers, or 23 minutes, and that's almost an hour for signals to get there and come back, and there's all the processing and relaying that happens in the meantime. So of course, real-time communications, or popping open an SSH connection, is not an option. But how does this network even work in the first place? Well, they've got the massive Gladstone antenna in the United States, another one in Australia, at Canberra, and another one in Madrid. And what this does is they have overlapping signal, which means that Mars always has at least one antenna pointed to it at any one time, and where they can maintain constant communications. And once you're on that side, you can take advantage as a rover on the surface by using the Mars Odyssey, or Mars Reconnaissance Orbiter, or the ESA-built Mars Express orbiters, which can all relay communications back to Earth much faster. So some of you might be thinking, is this an opportunity for software-defined radio? Can we use dongles that are cheaply commercially available to pull data out of this system the same way we do from weather satellites? And the answer is absolutely not. If you look at the Gladstone antenna as an example, this thing is 70 meters across, and even if you could plug your SDR into it, you'd probably need to cool your SDR down in liquid nitrogen to get it sensitive enough to be able to pick up the signals required, especially if you're going to communicate with even deeper space probes. So when it comes to new ways of putting yourself in jail, this isn't an option I'd recommend. So let's consider the last system requirements we're going to have here, specifically the display and the keyboard and mouse. And I know what you're thinking, the rover doesn't have any of these things. And if you look inside and consult the spec sheet, you will find that it can handle something called compact PCI. Now, this is not your regular PCI that you might remember, but more a backplane like this that all those boards plug into. So if you did find this rover, or you used the one in the Mars yard, you could plug one of these into it and get some HDMI outputs, but that's probably not feasible for what we want to do. And for fun, we can think about what we could do with that laser, but it wouldn't be a feasible way of projecting anything anywhere or actually using that as a display. So Doom's Linux version actually uses the X Windows system, and here's typically what it looks like. So when you run that, it starts up X in the background, which is the default Linux window manager, and there you've got it working in an X window. Now, one of the things I want us to consider are demos, and Doom has demos where it records key presses. And one of the ways in which you can do this, and this was a very popular way of distributing files and demos of how people had done things in Doom. But anyway, if you want to record your own one, this is my compiled Linux version. I just tacked in there record, and here I'm shooting some zombie men. I'm recording to a file called my demo. And notice that I've included just a little bit of more output, so whenever I fire the gun, it says weapon fired. You press key to exit. Don't worry, that's not an error, but you do have that LMP file. And if you just go double check by doing a quick ls on the directory where we've been running Doom from, you'll see we've got this file, and it's quite small. So awesome. How do we play this back? Well, you're just going to tack on the play demo option and refer to the file. Now you must remember to always take the extension off, but here I'm not touching the keyboard and it's playing through exactly the same demo that we had before. And that's pretty useful. That might be a viable way of running Doom on something if we didn't need the screen. So let's take a look at that. I made some modifications to the source code and added a new option called no display that I could add. And I could then run this and not get X up or initiate any of the video stuff, but still run the core game. So if I run this now with no display and I play my demo file, meaning I don't need a display or a keyboard now at all, notice that it's not bringing up anything, but it is busy playing the game and running the renderer and everything else. It's just not displaying it to anything, and it is running in good time. So I've put this all up on my GitHub repository for the Mac version. I'll port it over to PowerPC soon, and yeah, that's something fun to look at. So at this point, we can probably safely say that the display, sound, and keyboard are not even required, and this whole thing of running Doom on a rover is probably plausible. So finally, I'd like you to consider that many years from now, somebody somewhere is going to find one of these rovers, and they're going to look at the memory of those rovers, and wouldn't it be grand if they found something more fun than just a plaque or a golden record, but actually an interactive piece of history that they could play with and mess around with. It even comes to mind that if maybe aliens or someone hostile had to find this, they could have some fair warning about what we here on Earth are all about and what we're into. But yeah, with that, all the best to the Mars 2020 Prosperity rover. I've got my name on that rover. I'm one of the almost 11 million people who's made my mark on that. And I'd like you to encourage what kind of mark you want to make and what kind of mark you want to leave. That's it from me. Here's my GitHub and Twitter. Enjoy the rest of your conference.